Okay, all the stuff. There is a lot of stuff here. Software lab number 4, that's the third lab, but it's the fourth one listed is this week. We have the last lab next week, Monday and Tuesday, and then we have a midterm on Wednesday evening. It's in 277 Corey, across over there. There is a homework that is due on Thursday, but we are not going to post a new homework. What we would like you to do is to, instead of doing the homework, study for the midterm. So this is your first kind of a break. It will be, these homeworks are going to be coming now more spaced out. You'll get a homework approximately every other week. Do you feel relieved? There is much more material though, so you're encouraged to continue studying, solving these problems on your own. We'll have several review sessions. They're posted on the web, so you can practice. They'll be practicing midterm problems from the past for you. Please come to the office hours with the questions. My office hours are really, very few people come. Where is Mark? Did he drop the class? I guess that's what happened. And so he had some overlap. Please come to the office hours. You can learn a lot. I mean, those of you that come to the office hours, I don't see the faces here, but those of you that come to the office hours, I think we'll learn a few things when you show up. So do come. I do want to meet you also. I'm not that scary in person. So I have an office hour that I moved my office hour from Thursday to today. So please come by at 2 to 3 today or on Monday next week. That's it. And I've confirmed this Intel visit. We have gotten the bus. By the way, it's not going to be a football bus, unfortunately. It's a rented bus from outside because apparently we have gotten rid of those buses during the past few years. They have been too expensive to maintain. So we are leaving, the bus will be at 8 a.m. and we'll leave at 8:30 sharp. So if you're late, if you show up at 8:31, the bus is gone. So I'm assuming that everybody is going, and I'm going to, sometime before that, we're going to distribute those waivers because I need to sign a waiver that you're willingly coming on that bus. I'm not kidnapping you or doing anything like that. And the people on the other side are also excited because they see you as potential employees this year, next year, in 5 years, anytime, because they do have a shortage. So they'll treat you. If you have a resume, you'll get a pretty nice lunch and other things. I mean, if you give them a resume, that means they'll be pounding you with emails. Eventually, emails about, have you graduated yet? Are you interested in a job? But again, that's not too bad thing. I mean, it's better than sales at Best Buy that I get. Okay. Do you have any questions? Okay. Amazingly, no questions. So what happened last time? You guys talked about the buffer sizing, which is an important lecture. And please make sure that you understood it perfectly. So if I wanted to drive a delay, to drive a load with a minimum possible delay and no constraints given, how should I size the buffer chain? Before you do the fan out to 4, no constraint on input capacitance. You'll do it in one inverter of infinitely large size, as big as you can put in. But usually that's not good because somebody has to drive that inverter. It's like shoving all the problem to the previous stage. So if you have an input capacitance limit and output capacitance limit, how would you size that driver? You will put that many inverters that will drive that load with a fan out of 4 from stage to stage. How many inverters will there be? Log 4 of the ratio of output to input capacitance. It's a very powerful result. You'll find out that we'll be able to generalize it. And by using that generalization of that result, you will be able to design by hand an optimal logic path without using SPICE. And then we'll verify it in SPICE and find out, wow, it's awfully close. So what am I going to do? By the way, midterm covers up to today's lecture. Next lecture is not in the midterm. So, we are not going to test you on the stuff that you have just heard next week. So midterm is up to today's lecture. And then we talked about the energy. And I'm going to quickly recap the energy and then talk about the wires. I've given you a lot of stuff to read. This is about the wires. We're not studying everything. We're not really talking too much about distributed lines, transmission line models. But I would like you to start reading the CMOS logic, because we will do a first cut into that and then dive deeper in. But that all this stuff goes into the next midterm material. You will need it, however. You'll find out also these things that will start getting much easier because you'll be doing a project. As soon as we're done with the midterm, guess what? We get to start the project. You will get a practical feel for the things that you're doing. Any questions about the material? Okay. CMOS power dissipation. Remember, there are generally 4 components of the CMOS, of the power dissipation in CMOS. There is a switching power. And help me, what is that switching power? What's the value of it? It's full CV squared taken out of the supply. Half of it gets dissipated on the pull-up transistor. Half of it gets stored on the capacitance. Then when we go from 1 to 0 transition in the output, that charge gets dumped and we lose that second half of the energy. So essentially in each cycle, 0, 1, 1, 0 transition, we pull out CV squared out of the supply. If the circuit is sitting idle, does it dissipate any switching power? No. So at this moment, if this thing is sitting idle, should it be dissipating power? No. If it is really idle. Then there is leakage power, and we'll talk a little bit about that. And then there is short circuit power. It happens during the transition that, remember how we drew these voltage transfer characteristics, that during some short amount of time, both NMOS and PMOS transistors are on. And some amount of power is going to go, some amount of current is going to flow through both NMOS and PMOS. And then there are static currents. We said that CMOS does not have any static current, and that is still correct. But there are things that are needed in digital circuits that make digital circuits work. We still need some kind of biases often, and those things that provide biases dissipate a little bit of current and stuff like that. That is typically not implemented in static CMOS. Let's talk a little bit about the leakage power. Right, what happens here is that transistors are imperfect switches. Ideally, when the switch is off, there should be no current flowing through it. But this is an electronic switch, and some current leaks through it. So, what happens here? So, when input is at VDD, output is at 0, current leaks from VDD through PMOS transistor and to a ground. Similarly, when input is at 0, this transistor is on, VDD, output is at VDD, and this transistor will leak. How much is that leakage current? Well, in addition to transistor leakage, there is also diode leakage. We have these reverse biased diodes at the drain. So if this is a drain of the transistor, on the wrong way. So this is a p-type transistor, right? So you would have a p-n diode this way. You have a reverse leakage current going that way. It's of the order of, tens to hundreds of picoamps per micron squared. And it does increase with at higher temperatures. There he is, see? We were missing you. And we've been criticizing you for not coming to office hours. All right, I'm kidding. I'm sorry for picking you. But this is generally much smaller than the transistor, the current the transistors leak when they're off. It used to be actually about the same or order of magnitude as the off current from the transistors. But off current of the transistors has gone up a lot. So why has this off current gone up so much? So this is something that was shown, this is something that is approximately your class process. This is 90 nanometers CMOS, showing that it is leaking something of the order of tens of nanoamps. So why have the leakage currents gone up with scaling of technology? And by the way, here is, before we dive into that, here is what is happening. This is that plot that I've plotted before. It is IDS versus VGS. And the way how we plotted it before, it used to look like this, right? VGS, IDS. And it looked like this. It was flat up to the threshold, and then it was something quadratic, and then kind of linear up. So this was VT. Okay, here is what is happening. What is the value of VT, approximately? Somewhere around 0.4 volts or so, a little under 0.4 volts over there. So here is VT. So what happens here? It's easier to see it probably going from high voltage to low voltage. So when you're going from high voltage to low voltage, the current on log scale decreases slowly because it is linear. When you're taking a log of something that is linearly decreasing, it is decreasing slowly. And then it reaches the threshold. And instead of dropping down to 0, it starts decreasing much faster than linear, but still exponentially. Okay? This looks pretty much linear, meaning that the current is decreasing in subthreshold exponentially. Right? Log of exponential is linear. But it does not go to 0. Okay. This number used to be much lower, down to the 10 to the minus 13th or something like that, fractions of the picoamps per micron. So this is per micron of width. Why did these currents go up? VT is lower, and it does not have time to go down. Right, I mean, VTs in all times used to be 0.7, 0.8 volts or something like that. And, you know, you had a few more orders of magnitude to go down. Now we have had to drop the supply voltages while dropping we had to drop the threshold voltages while dropping the supply voltages. And as a result of that, the leakage currents, these off currents, have gone up. What is this? This slope is something that is very important. This slope is called the subthreshold slope. What is it dictated by? We have it much more discussed in the next slide, but let's talk a little bit about it. That tells us how well is this transistor turning off. What is the subthreshold slope proportional to? You've probably seen that in some of these in some other classes, right, that you've had. What is it dictated by? What is the ideal? What is the best subthreshold slope that we can get in a typical CMOS device? It's about 60 millivolts per decade. It's proportional to this Einstein's constant, KT over Q. Now, it is a little bit higher here. So what you find out here, it drops by 1 order of magnitude here, 1 order of magnitude, in a little less than 100 millivolts. So say about 80 millivolts. So it is higher than the minimum. The slope is a little bit worse, right? We need to spend more millivolts in order to turn it off by an order of magnitude. And the fundamental reason for that is that this current comes from this bipolar transistor, parasitic bipolar transistor that is sitting underneath and is leaking. We would like to turn that bipolar transistor off, but we don't. What happened here? The subthreshold slope is a little bit worse than what would happen to an ideal turnoff of a bipolar transistor. Ideal turnoff of a bipolar transistor will be proportional to KT over Q. So because we don't have, right, there is a gate, here is a channel, but we don't have this access to, directly to the base of that transistor. We are pressing that base through a capacitive divider. So if you draw this thing, it looks kind of like this. We have this capacitance, and I would like to turn off this transistor that is sitting down here. But I don't have good access to its base. I'm accessing it capacitively through a capacitive divider. And you'll find out that this subthreshold slope is essentially equal to KT over Q times this capacitive divider. And that's what you get here. ID is proportional to I naught times Q times VGS minus VT times NKT, where this N is the ratio that comes out of this capacitive divider. I don't understand what is going on here. So this subthreshold slope, 1 over subthreshold slope, is equal to the amount of voltage that we have to reduce the gate voltage by to lower the leakage current by an order of magnitude. And that's how it looks like. So typical values are, ideally it would be 60 millivolts. Typical good transistors are sitting somewhere between 75 and 90 millivolts per decade. If it goes over 19 millivolts per decade, it's a pretty bad, very leaky transistor. Okay? Okay, if you plot it the other way, if you plot IDS versus VDS, and again, this is plotted per micron. What we see here is how does this leakage current look like versus the drain to source voltage. So what we have here is a standard bipolar current here. This looks like a bipolar transistor that you have seen. This is with VGS equal to VGS being 0. So you have this bipolar conduction, but it kind of bends up and starts becoming more exponential. That exponential increase is because of this drain-induced barrier lowering. What is happening is that this diffusion current is increasing because the barrier is being lowered by the drain side. The threshold is dropping, and it drops exponentially. This is how a transistor in your project looks like. When you take a look at Intel's fast transistors, this increase that was here by a factor of, 5-ish or so, is more like 100 in very high performance processes. So your leakage current from low supply voltage to high supply voltage will increase by more than 1 order of magnitude. How can you reduce leakage currents? And there is a very simple way. If you can operate stuff at a lower supply voltage, particularly when transistors are idle, you can cut down a lot of leakage current. Do you have a question? No, this is linear. And I had to remove the axis, but it's about 10 nanoamps in this kind of a process. This is linear. So what you'll find out, this is one of the things that we don't talk much in 141, but half of the class in 241 is spent on that, is what do we do? How do you cut the leakage? I mean, if I had all my transistors leaking tens of nanoamps, and you will see some modern transistors leak hundreds of nanoamps. And I have 1 billion transistors on a chip. What would be the leakage current of this whole thing? 1 billion times 100 nanoamps. 1 billion times 100 times 10 to the minus 9. 10 to the minus 9 times 100. Yeah, it will be 100 amps. And I can assure you there is 1 billion transistors in here. Do you think this leaks 100 amps? No, it doesn't. Neither does this microprocessor. What do? But how do you turn stuff off if it does not want to be? This is when the transistor is supposed to be off. This is what is it doing. So how do you turn it off better? Removes the power supply. Okay, using some better switches, remove the power supply from, and you won't leak now if I remove your supply. The other things, what you'll find out, the parts of this chip are awake, and they're waiting for me to click this thing such that the display comes on and so on, or for the call to come in and it starts ringing. those parts are going to be, but they don't have to do anything really fast. You know, you won't notice if the response time is 2 milliseconds or 200 milliseconds in these situations when it's waiting for a wake up. That stuff will run at a low supply. That would cut down the leakage current. Yes? There are things that can be made to run much slower at lower frequencies, for example. Yes? You can make some transistors have a higher VT, that's correct. But again, not that much more higher. So again, you know, mobile devices will operate with a higher VT than what we see here. But that would cut, you know, these thresholds are spaced by about 100 millivolts. That would cut the current by 10x. So instead of 100 amps, we would have a 10 amp leakage, for example. No, you have to do much more, and that's what most of you will be doing when you get employed and get design jobs. You will be cutting the leakage one way or another. Or creating it. Some of you will be creating the leakage, some of you will be cutting the leakage. Okay, makes sense? There are a few other things. The threshold varies with the channel length. So there are a few things that happen here. You know, I'll talk a little bit about that. You know, long channel threshold is a little bit higher than the short channel threshold. But in modern devices, like the ones that you have in your process, there'll be something that are called reverse short channel effects, and it'll look like more like that. So this will be somewhere around here will be a nominal channel length. If you vary the channel length, you will end up with devices that have significantly higher leakage. If you, because of the process variations, you end up with the shorter devices. Or if you make them longer, they'll again have lower threshold. And things like those too. I mean, this is just for your informational purposes. And that's it. Do you have any questions about the leakage? Because of there are things that are called reverse short channel effects. And these are the things that halo doping that was put into the transistor to protect its integrity is a little bit farther apart now when you make the channel length longer. For example. Okay. Is this clear about the leakage currents? We are not going to spend too much time on the leakage currents, but it will be for your informational purposes. And by the way, this course is due for an upgrade or overhaul in some parts, because some things that we teach in this class, we don't do it commonly anymore. So we may throw some more leakage stuff in the next offering or the offering after that one. Okay. The next important topic is the topic on wires. So what are the wires? So we have been talking about the transistors so far. We use wires to connect these transistors. And transistors form logic gates, and in order to get a logic function, you have to connect many of them, and then you use wires to do that. The wires in integrated circuits are very important, and they have an increasing importance. Wires are also called the interconnect. That thing that you have in between the gates, and here shown as simple buffers or inverters, these pieces that connect them are three-dimensional physical objects that look like that. And much more complicated than that. These physical objects tend to have their physical properties or electrical properties. And for our purposes, there are capacitance, resistance, and inductance, all of them affecting some of the key performance metrics like delay, power, Leakage? No, wires don't leak. Luckily. There is. Won't leak. It's a pretty good dielectric. I mean, there will be a dielectric leakage, and you won't have that that leakage, right? So wires are important, right? They contribute to something. You know, you'll find out. It's like, depending what kind of a design you have, 30% or 50% of the overall delay is because of the wires. You know, you design something and you don't put the wires in. You simulate it looks good. You put the wires in such that the things are connected, wire models in, and things got 30% slower or 50% slower. And then you have to redo everything. You'll also find out that, you know, it may be at 30% of power or even more may be going into wires. Okay, so let's talk about those properties. So wire models, you know, if we were to model all of the wires, we would have to add the resistance for each segment of a wire, inductance, and the capacitance. That would be really complicated to analyze. Usually what we'll find out, we will be adding capacitances only. So these are 3 wires running in parallel. What we would find out, for each segment here, we will try to add some capacitance that we care about. And we'll be adding capacitances between these wires. In the first approximation, we'll be we will not be counting resistances. And we will not at all in this class be talking about the inductances. But what is a general rule of thumb? Where can we ignore the resistance of the wire? When it is smaller than what? It's smaller than something else that matters. When it is less than, you know, there is usually something driving this wire. There is a gate driving that wire. If the resistance of that gate is significantly smaller, if the resistance of the wire is less than the resistance of the gate, then we will be ignoring it. So for things that are close together, we can usually neglect resistance. But we do have to account for the capacitance. For things that are farther apart, we'll have to account for resistances as well. And you'll find out in real designs, for very, very long wires that go across the chip, we'll have to account for the inductances. Okay, I've talked about that. Yes? There are rules about ignoring inductance. And they're discussed in the book. I'm not going to dive into that now. You'll find out that inductance is really important for power supply lines and for clock networks. And I can show you some illustrations at some point if we get into that. How does it matter? But for now, let's just focus on the capacitance and resistance, because that's what I can cover in 35 minutes or so and be done. So when we talk about the capacitance, right, we have looked at an inverter, and we have seen 2 important properties. It has the input capacitance that is primarily set by these gate to source voltages and some amount of CGD. There is self-loading capacitance here of the previous gate that is primarily set by drain to body capacitances, and C, and the overlap capacitance between the gate and the drain. And we have done that optimization of a buffer. You had self-loading capacitance, you had the load capacitance of the following gate, and you knew how to optimize it. Now, usually what will be in between them is a piece of a wire. This wire has its own capacitance. It has to go into that whole model of calculating the delay. Okay. Well, then how do we find out what is the capacitance of a wire? Well, when you look at the wire is typically implemented in one of the metal layers. It can be implemented also in polysilicon or in diffusion, but typically will be implemented in a metal layer. This metal layer, one day stadium will be done. This metal layer is a three-dimensional structure that we have that forms a capacitor between itself and the layer below. See, if it is the lowest layer metal, it would form a capacitance between itself and the substrate through some kind of a dielectric that is placed in there, oxide typically. And this capacitance, to the very first approximation, is equal to the parallel plate capacitance between the bottom plate of this capacitor and the substrate. And it's equal to epsilon times W times L divided by the thickness of the dielectric. So, which simply means the longer the wire, the more capacitance. The wider the wire, the more capacitance we get. Okay. And what you'll find out, there is, depending on what is this dielectric that is in between. So typically, in the old times, it used to be silicon dioxide down there. These are the things that correspond to what we have on chips now. These oxides, it used to be a very convenient thing. I mean, you put one layer of interconnect and then put a little bit of an oxide, and it's nicely isolated from the next layer, and you keep stacking them. But this is kind of giving us too much of a capacitance, or a wire capacitance, so people have been working on reducing that, using things that look like aerogels and things like those, getting very close to this free space, epsilon r. So what you'll find out typically in chips today are these relative permittivities of about 2-ish or less. Yes, question? They have been integrated into a fabrication process. No, the material scientists have to earn their salaries too. Yes? Does not, there is no one-to-one relationship. That's why material scientists can design that. I mean, the breakdown depends on the number of defects that they get in there. If they have cracks and the field starts going through. The other thing that is important, these are three-dimensional structures, and what you're going to find out is that this capacitance is, nowadays very rarely limited by this bottom plate capacitance, parallel plate capacitance. A lot of it corresponds to this fringing field capacitance. Now, fringing field capacitance is hard to calculate. There are some formulas over here given for round objects and so on. We usually don't try to run these integrals and try to calculate that. Instead of that, we'll just give you numbers. And what you're going to find out very quickly here is when you're calculating the wire capacitance, you'll be given a few parameters down here. This will be given as, so C wire is going to be equal to the C parallel plate times the width and the length of the wire, plus you will have fringing field capacitance here, times, and it will be given per unit length, times 2L. because you have fringing field on one side plus fringing field on the other side. I put this in, this is a wrong slide. This will be a very simple exercise to do. And you'll do it typically as a designer. You'll actually memorize these numbers as a designer, and you'll know exactly what is the capacitance per micron of length, and you'll know approximately what to account for. So what you have here is are the amounts of capacitance in a quarter micron process that correspond to the top plate and bottom plate. And this would be parallel plate, and this is fringing field. Values, remember, parallel plate capacitance are given per unit area, fringing field per unit length. You'll find out that these capacitances from, I messed this up, this is top, this is bottom. You'll find out that the capacitance between poly and field oxide is that. Poly and active is going to be given by some, no. Did I mess this up? Wait a second. So yeah, this has to be bottom, right? So then you have poly. There is no poly and poly. There is aluminum and poly, aluminum 1 and poly, aluminum 2, and poly, aluminum 2 and aluminum 1, and so on. The farther the spacing between the plates of a capacitors are, the less of a capacitance you got. Now, there are a few things. In real life, this is the structure that you're going to have. There'll be multiple layers of wires sitting on top of each other. And how are you going to assign these where will be the second side of this capacitor? Parallel plate here. Will this be fringing field to the other one, or a part of this fringing field will go down? Will there be a capacitance here too? How much of this fringing field closes down to the next wire? How much of that goes down? How would you figure that out? Yeah, but how do you know how much does it go to each one of them? It will be, right? I mean, there are capacitances in all ways, and you usually cannot do this by hand. What you can do by hand, relatively easily calculate the capacitance for a long wire. What is the total capacitance for that long wire? And that will be the worst case estimate. You will typically have a program that is doing the extraction. And you have seen some flavor of it. And there are simple extraction programs and very complicated extraction programs that can do this appropriately. Some of them will do it simply by applying a certain set of rules. There are some of those that are going to be solving three-dimensional Maxwell structure here and getting that capacitance for you. You usually do not do that in digital circuits because we cannot track all of that. That's what analog people do when they need to extract their inductors or things that are complicated. There. Okay, a few things about the impact of capacitances. What I wanted to say here is distracted. I wanted to say something to take a different course of discussion, but I got into this way. Capacitance and delay. See, I have 3 inverters driving some load, and say I have, I don't care what, these are going somewhere, and I have some load over here that presents a total load capacitance. And I have a fairly long bus that goes over a 0.5 millimeter or a millimeter of a length. And I have some coupling capacitance between these inverters. So if this signal goes from low to high, this output will go from high to low after some delay. How is this delay? How would this delay be affected by the transitions on these wires? Yeah, we may see either no effect or double effect because of the Miller. Let's try to draw that quickly, right? So if this signal is sitting at 0, this one will be at VDD. I essentially have to switch every single one of these capacitors. I have to charge them together with this one. So this total capacitance is going to be equal to CL plus CC1 plus CC2. That will be case 1, right? Similar situation happens if this capacitance is, if this input is at VDD. What happens if this input instead follows the same way, goes from low to high? What's going to happen to these capacitors? Well, this value, this wire will go from high to low. So these coupling capacitors are going to go simultaneously down, but not because of the action of the wire that we are looking at. It's because of the neighboring drivers. What's going to happen as a result of the delay? Go down, so it does not have to be, the capacitor is not discharging. Both of them are changing the value, so this signal would advance. We'll have a less of a delay. Make sense? Because it's driving less capacitance. Also, what you'll find out, because of the coupling between these wires are going to help a little bit. On the other hand, if you have a situation where this signal is going in the opposite direction of the transition on the wire that you're looking at, you're going to have a little bit of a retardation of the signal, right? So that will be the third case, C total. second case would be total is equal to CL only. So depending on the neighborhood of on the neighboring signals will be affecting the delay of a wire or of a signal depending on the transitions. How far does it influence? Well, luckily, if I have a wire and I'm looking at the wire cross section, most of the field lines from that wire are going to close on the nearest neighbor. Yes, it's a three-dimensional structure, and most of them are going to close on the nearest neighbor. The things that are farther out will be much less affected, yes. Oh, both of them. I'm thinking that both of them are switching, right? Both neighbors are switching at the same. Both of them are quiet. Both of them are switching up. Both of them switching down. I could have probably deleted one, but yeah. That's essentially it. So how are you going to deal with this? With this thing that your delay is not dependent only on you, but on your neighborhood. You will get the worst case scenario. So typically these simulators are going to give you worst case, best case conditions. In hand analysis, how are you going to handle it? You're not, unless we set you up with some kind of a problem. Make sense? Do you have any questions? Okay, the second topic that we care about, the second component of the interconnect parasitics is the resistance. Now, first, are we clear about the capacitance? How are we going to extract the capacitance? We know the parallel plate. We know the fringing. That's it. We'll take the closest neighbor for all the fringing stuff. If you have a parallel running wire, all the fringing capacitance is going to end up on the neighboring wire. It's not going to go down to the bottom layer. We'll see the examples of that. Resistance. So sometimes we have to care about the resistance. Okay. Resistance is, so if the current is flowing through a wire that has width, height, and length, like this, what does designer have access to? Well, you cannot change the thickness of a layer in an IC, so the only things that you're changing are the things that you see from the top. Width and length. The resistance is known that is equal to the resistivity times the length divided by the cross section of the wire, which is the height times the width. So if the current is flowing in this direction, and this is the width, and this is the length, you'll find out that typically the resistance is given as the sheath resistance, because these two things are constant. And length and width are those things that you're changing. You'll also find out that the sheath resistance is typically given per square, because these two squares are going to have exact same resistance. If I make a square twice as wide and twice as long, it is going to have exact same resistance. What's going to happen to this square's capacitance, though? will be 4 times bigger approximately. Almost 4 times bigger. Because the fringing capacitance has not gone up that much. Make sense? This resistance will also be given as R per square. Some time ago, most of these resistances, most of the wires have been implemented using aluminum. Somewhere up to a quarter micron, 0.18 process, and so on. It used to be relatively convenient. Nowadays, most of this resistance is, most of the interconnect is implemented using copper. There has been a transition to copper because of the lower sheet, because of the lower resistivity, right? Because it's a better conductor. Why didn't we start with a copper? Too expensive is, but it's not that much copper in there. It's a little bit harder to etch, but people have figured that out. Yeah, copper is difficult. It tends to diffuse into things. So they have to figure out a way how to put it in there and it does not diffuse everywhere. So it has been a major breakthrough 12, 13, 14 years ago when they developed this dual Damascene process. Do you know what Damascene is? Anybody has roots in the Middle East? There are these, they have these beautiful ornaments that originate to the city of Damascus, where they etch copper. So there are people who can etch copper. They have figured that out approximately 2,000 years ago or so, 3,000 years ago, how to do these relief structures in copper. And they use that for shields and things like those. Well, they're using similar process for wires here. They basically etch the structure in the oxide, in the dielectric, and then put some insulating layer that stops the diffusion of the copper, and then fill it with copper. Both, they call it dual Damascene because they fill both the vias and the wires in the same step. Where is Damascus? Syria. Did they invent the dual Damascene process? No, IBM did. It's, but similar stuff that they've been doing for the past 3,000 years or so. So we have had a change of added lower resistivity materials. What is the other way how we can lower the sheet resistance of a material? By looking at this equation. Increase the height, use thicker wires. But what's the problem with thicker wires? Yeah. So here is what happens with the scaling of technology, right? My bottom, the lowest layer metal, when the transistor shrinks, that. if there is a wire going on top of it, what should happen to this wire? It has to shrink. So this wire would start looking like that, because it has to meet the contact pitch. I mean, it eventually has to be able to connect to these transistors with enough of a density. If I don't shrink, so first, what happens here what happens with the sheet resistance going from here to there per square? It has increased. If we wanted to keep the sheet resistance constant, what should I do? Make it even taller. Becomes a processing problem to put wires that are really skinny and really tall. So we can't do that. So what do? Different thicknesses depending on different metal layers. So essentially what we have seen for a while, it has been happening with each new technology node. The bottom layer metals have shrunk, the top layer metals have not. And they've been adding, in order for this to make sense, they have to add metal layers as they do that process. So because the top ones, we don't want them to be very resistive, because they're used for the things like power distribution and clock distribution. The bottom ones are being used for local connectivity. So what you'll find out, the bottom layers are thin wires, thicker, and then you get a little bit wider and wider. M1, M2, M3, M4, and so on. Yes? A good question. So, right, in order to do, I need more layers in order to have this appropriate wires to go to appropriate lengths. So local interconnectivity will typically be done with the bottom 4 layers, because you need to, you need a few layers to avoid congestion over there. So you go, and those are the basic rules that you've probably seen already in the labs, and it's a good idea to stick to that. Metal 1 goes horizontal, metal 2 vertical, metal 3 horizontal, metal 4 vertical. You should be able to connect pretty much everything locally by doing that. Well, then you want to go longer routes. And then you do that, metal 5, metal 6. And then another layer for power and ground distribution, and very long across layer wires are going to be metal 7 and metal 8. They'll typically come in pairs. They'll have a pair of thicknesses. This is kind of how it looks like. This is a 90 nanometer process, similar to what you have. Transistors are down here, and here are the plugs. And here is how these wires look like. So bottom 1, 2, 3, 4 are kind of all looking like each other. Then you have these intermediate ones, 5, 6, 7, and 8 and 9 are real thick. Excuse me? No, what is the darker region? No, I think these are actually the wires. And this. Where in the middle? This? Yeah. These are the contacts, right? So this is a stack of contacts via from the top metal layer down all the way. This is how a via looks like. These are vias. Down on the bottom are transistors. You don't see them. There's no silicon. This is insulator here, the electric. That's the wire. These are the vias here, right? So you need to connect somehow to the next layer. And the vias are not perfectly square. They look more like cones, pyramids. It's from the process. This is a Damascene process also. You can see this little layer, this white thing around is what stops the diffusion of the material. So what you'll find out, sheet resistance is, less than an ohm, 0.1 typically, or 0.05 ohms per square. And that's what you would like to do, the routing. Sometimes you have to do routing in some other materials. And it's really bad if you have to do it in the diffusion or in the polysilicon in older days. Modern processes, however, are all silicided to allow you to do short routes of in polysilicon or in diffusion. But keep in mind the resistance, even in silicide. Do you know what silicidation means? Typically, diffusion or polysilicon are relatively high resistance conductors. What they do, they dope them, typically their surface, to get lower resistance. They do it because of digital guys, to lower the to allow local routing. You can route a little bit in poly, like connecting the PMOS transistor and the NMOS transistor in an inverter. That little piece of a wire is done in a polysilicon. Or you can connect things in a diffusion. But analog people hate that silicidation. Why? They typically like resistances that are more than a couple of ohms. And this eliminates all the resistances. They want a 10 kilo ohm resistor. Well, in order to make a 10 kilo ohm resistor, you have to make it really long. Okay? I'll stop here because I'm running out of time, and we'll pick up in interconnect modeling just a few slides on how do we calculate the delay and Elmore formula and stuff like that next time.